Hello physicists and welcome. In this session we'll be looking at the T2C1 balance forces simulation. In scenario 1, what you had to do is look at the interaction diagram and force diagram for a collection of objects that were being pushed but not moving. We see our speed is 0 in this case. We can see that SimMan is pushing on the crate to the right with a force of 485 newtons. Because our forces are balanced, there needs to be a frictional force of 485 newtons to the left. How do I know they're balanced? Because an object at rest remains at rest unless there are unbalanced forces acting on it. And we know there's other forces acting on this that aren't explicitly mentioned, but we can figure those out. Let's go ahead and make an interaction diagram and figure those out. Okay, so I want to list my non-contact forces, gravity, my contact forces, normal, tension, and friction. Hey, the object that for gravity that we're interacting with is the Earth. So let's go ahead and identify those things, the crate and the Earth, and the refrigerator and the Earth. Let's go to our contact forces. Any place where two objects are pressing against each other. I can see between the crate and the ground, the refrigerator and the crate, and SimMan and the crate. Let's go ahead and put in our lines here. You notice I'm not listing each of the letters on our interaction diagram. That's just for clarity and to avoid clutter. I don't see any tension here. I'll skip that. And the last thing we see, it's listed here in the big red arrow that we know that there is a frictional force between the crate and the ground. Let's move on to our force diagrams. Remember, for each one of these loops, we have to account for a force. Okay, so this is what I got. If I see the crate, and let's go back to the crate. We see that the crate has 5 forces acting on it. Hey, I see here I have gravity down. I have SimMan pushing to the right. I've got the normal force pushing up. I have the refrigerator pushing down. And I have friction acting against its motion to the left. 5 forces. I see those are reflected here in my force diagram. So on the left is the force diagram for the crate. We have 2 forces down, 1 force up, 1 to the right, 1 to the left. Most of these are given to you explicitly or can be figured out pretty easily from the mass. There's one force that's a little more challenging, and that is that bottom force, the normal force on the crate from the refrigerator. To figure that out, we have to look at the force diagram for the refrigerator. And let's take a look at that. Okay. Hey, we know that the force of gravity on the refrigerator was 2,000 newtons, 200 kilograms times 10 newtons per kilogram. So I know that the normal force is 2,000 newtons to balance that. Well, if the refrigerator is, sorry about that for that delay. Our refrigerator is experiencing a normal force to balance that gravitational force downward. The gravitational force, you probably figured out, 2,000 newtons. That's at 200 kilograms times 10 newtons per kilogram. So we have to have a 2,000 Newton upward force. The only source for that force is the crate pushing up on the refrigerator. What's the pair to that force? For every action, that normal force of the crate pushing on the refrigerator, there's an equal and opposite reaction. The refrigerator pushing down on the crate. We can see those, the 2 circled values, and that is our Newton's third law pair of forces. And let's take a look at this for the situation where we're sliding along at a constant velocity. Notice in the upper left-hand corner here, we're moving at a constant velocity. Because we're at a constant velocity, we know that our forces must balance. We'll go ahead and make an interaction diagram for this. Again, gravity acts between the crate and the Earth, between the refrigerator and the Earth. Let's look at our contact forces, normal force, anywhere 2 objects are pushing against each other, and you'll see that these are the same 3 forces and position forces we had when it was standing still. We don't see any tension force now. The last one is friction. We can see there's a big red arrow pointing to the left that indicates it's there. Plus we know we have to have balanced forces. So if we're pushing to the right, we're moving at constant velocity, there has to be something to the left that's balancing that force. Let's make the force diagram. If you take a look at the force diagram, it looks very much like our situation where we were trying to push, but it was not moving because our forces are balanced. You may find that your numbers are slightly different here for your normal force from SimMan and your frictional force, but the general look of your forces or the force diagrams will be the same. They also, again, have that pair of forces. Force normal on the refrigerator from the crate is the pair force to the force normal on the crate from the refrigerator. Equal in magnitude, equal in type, opposite in direction. That's our third law pair. All right. Hey, the last situation, we have our crate and refrigerator sliding along our frictionless road. How to become frictionless? You can see it's covered in ice. Right. It's moving at a constant 24.1 meters per second. We'll see if we can put together that same interaction and force diagram that we did before. Hey, we have our gravitational force, a normal force, frictional force. But let's look at this a little more closely. If SimMan is not pushing, we have to get rid of that normal force between SimMan and the crate. And if there is no friction, our frictional force will disappear. Let's take a look at our force diagrams. Force diagrams will look very much similar, except the forces that disappeared. Let's get rid of the normal force between the SimMan and the crate. And the last one to go, of course, is our frictional force. So take a look at those. Notice this again is a constant velocity. Our forces are balanced. They don't have to be balanced in the direction of our motion. They just need to be balanced. Okay, so for now, that's physics.